Okay, so last time before the break, we were discussing this lemma. We are trying to prove this. And we started the proof. We did half of it. If your one form is given in this form, actually any expression in this form is a one form. We discussed that. And for the other part, so whenever we have a one form, phi, it can be written in this form. So let's do that. Now, conversely, let phi be a one form on R3. Okay. I have to show that that one form can be written like this for some functions. So I have to tell you what are those functions for a given phi. Okay. So let's see that. Okay, so let just fi to be the function defined by this. This one form eating the vector field ui, I from 1 up to 3. Okay. Did I tell you what these vector fields? These are the standard vector fields. U1 is the vector field. Okay, let me say this way. Are defined by, we have defined these before. So at any point P, this is just 1, 0, 0. P, sorry, U1 is this. U2 is 0, 1, 0. P, and U3 P is 0, 0, 1 P. And my functions are just defined as the values of my one form on those vector fields. A function, sorry, a vector field is fed into a one form, gives me a function. So they are the functions in the statement of my lemma, right? I want to write this phi in this form, so I need these functions, fi's, and fi's are nothing but these functions. Now let's see why this is the case, okay? So we must show this, must show phi is equal to this expression, fi dxi, I from 1 up to 3. Now, both of them are some functions defined on R3. To show that two functions are the same, I have to tell you that they take the same value at each object, whatever they eat. In this case, they eat vectors and gives us some numbers. So I have to tell you that these two expressions agree on each vector, tangent vector. Now let's see that. Take any vector field. V, any vector field, we know that is a combination of this, standard frame field, right? U1 at any point P, let's say U1 is this vector. U2 is this vector, and U3 is this vector. So they give me a orthonormal frame at any point. Therefore, whenever you give me a vector, we had color chalk, but they're gone. Whenever you give me a vector, VP, I can write this VP as a linear combination of this frame or this UIs. So let's say this is just A1, U1, A2, U2, A3, U3. What are these A1, A2, A3? They are just functions where AI from R3 into R are just some functions. Are some functions. Because my vectors, of course, may change from point to point, right? It's a vector field, so it changes from point to point. All right. Okay. Ya da ilk önce şunu silene kadar o tahtaya bakın yine. Şunu sileyim. Okay. Sildim. Şimdi geçelim. Geçmedi. Okay. Yok şöyle. Fazla gitti. Okay. Now then we have what? Phi minus sum I from 1 up to 3 Fi dxi at on this vector field. My aim is to show that these are the same. So my aim is to show that this expression is equal to 0. Let's see if it is the case. Well, this gives me this object, right? These are just functions. I take the difference of the functions, apply to a vector. So I take v of, so phi of this minus this expression of v. Well, phi of what? What is this? This is u is just I from 1 up to 3 ai's, these functions times ui minus summation I from 1 up to 3 fi dxi, and then to avoid confusion, let me use another index here. Aj, right? My vector field U was the sum of AI, UI, right? But I use different index to avoid confusion. Now, what is this? This is a one form, and I know that it is linear at each tangent space. At the tangent space TP R3, this is a vector. It's a linear combination of 3 vectors. And I apply this linear transformation. It's a linear transformation on this tangent space. Therefore, I can write it this way. So this is just AI at the point P, of course. And then phi eating these vectors. And then here I have 1 to 3 What about this gadget? So here I have fi. All these things are happening at the point P, and then dxi eating this vector. The same thing. This is a linear object eating this gadget. So at the point P, these functions behave like constants. So I just take them out. And then I have, okay, I forgot writing the sum. Summation j from 1 up to 3, ajp, and then dxi eating this gadget. All right. Well, we will see that this thing is equal to, so this is canonical delta ij, which is 1 if I and j are the same, 0 otherwise. Why is that? Yeah, exactly. All right, so let's come back. Now, so that expression is equal to, so phi minus I from 1 up to 3, fi dxi evaluated on the vector field v is equal to, so this is just from 1 to 3 aip. And what is this gadget? This gadget is just by definition, right? We defined it here. We said, where was it? Fi is nothing but phi of ui. So phi of ui instead of phi of ui, I can write fi at p minus I from 1 to 3 fip, and then I have summation, but this is 0 unless I equals j, and when I equals j, it is just 1. So I have just aj, sorry, ajp, and then, okay, canonical delta ij, and here I have summation. Maybe I can write it this way, 1 to 3. And of course, this is 0 if I and j are different, and it is 1 if I and j are the same. So I have both terms equal to each other. This is just the same thing, FIP and AIP, so that this is 0. And why this is equal to canonical delta ij? Note that. What is this? diuj. This is just by definition uj applied to the function xi, right? This vector eating this function. And what was this? This is nothing but directional derivative of the coordinate function xj along the direction uj. So this is nothing but del xi del xj, okay, at the point P, well, as a function. And this is what? This is just either 1 or 0, right? If I and j are the same, it is 1, otherwise it is 0. Okay? So this finishes the proof. This is interesting in the sense that, although vectors and dual vectors, they form isomorphic vector spaces. So one of them shouldn't have advantages with respect to other one. But, when it comes to tangent vectors, one forms, their dual vectors and so on, actually forms are advantages because they behave nicely under functions, okay? And actually, this from even high school, right? In high school, you learned integration, and you have seen variable change. Variable change is nothing but, pulling back forms. So I'll do one example. Well, actually, they are elements of tangent bundle, but you mean, well, section is considered, it can be considered as an element of tangent bundle at each point. Okay, so I am not using that language. We say, vector field, it's actually a section of the tangent bundle, but we say just vector field. Orada işim bitti. Okay. This one? Well, phi applied to this vector. So I, can do this at any point P. At any point P, this is a vector and this is a linear object at that tangent space. Yeah, you are right. You are right. I compute this. This is a function actually. At any point P, I have this P here. I compute everything at the point P. At the point P, this is a tangent vector, and this is a linear transformation on that tangent space. So I can take these constants out. Phi eats these gadgets, and so on. Okay, let me. Okay, let me do one. So. Okay, let me do a couple examples. I am not sure if it is explained in the book at this point. Maybe they are explained later, but I think we can do it at this stage. Suppose we are in one dimension, okay? Not from R3 to R3, but from R to R. Any differentiable function.
Şu an göremiyoruz hocam. Tahtayı çevirmediniz.
I am sorry. Okay. If a differentiable function and suppose I have a one form here. Let phi be a one form on R. Diyelim ki şey olsun. Say phi equals. Zaten tek bir değişken var. I have only one variable. Suppose it is just dx. Okay. So what is a pullback of f? So by definition, it is the following. Now, f takes points to points, right? Suppose I have a point here. It is mapped to this point, f of x. And whenever I take a vector here, at the point, let's say, x, I get the vector field. It's the image under the derivative map. What is the derivative map? df from the tangent space at x into tangent space at f of x, it is given by the derivative of f. It's a one by one matrix. I can write its matrix notation. It's a one by one matrix. And what is this? This is nothing but derivative of f. Okay. So whenever you have a vector field, let's say v, I write v sub x to denote that this is a vector at the point x. It's just a vector. Its image is what? Its image, this vector. So df x at the point x, this is nothing but f prime x dx. Sorry, f prime x vx. Yani isterseniz şöyle diyeyim. Okay, let me explain this on a more specific example. Let's say f is just given by this rule. Fx equals 1 plus x squared. Okay. Then what is the differential of f? Differential of f at any point x is given by this. It's the linear transformation, and in the standard basis, it's given. The matrix notation is just this, so it is just what? 2x. At the point x, the derivative map is just 2 times whatever that point is. For example, if x equals 5, then differential of f at the point 5 is the tangent, is the linear map. 5'in görüntüsü nedir? 26, right? 1 plus x squared. And this map is what? This map is just, so, okay. df at 5. In matrix notation, this is just tan. because x is 5. So this does the following. If you give me a vector, it sends it to, so I may regard this as a 1 by 1 vector, right? Multiplied by 10. So here I have v. You just multiply by 10, so you get 10v. Yani türevi lineer bir map gibi görüyoruz, right? Derivative is a linear map at each point, okay? It's a field of, actually, field of what? You may think it this way, linear maps. At each point, you have a linear map. Okay, what about pullback? So f star of dx, what is this? Well, this was, by definition, this is, okay, this is just the vector. Okay. All right. Let's say, let us compute this at any vector. Let's say the vector u şimdi şeyde in R3 this ui's are, u1 is this, right? 1 0 0, and then u2 are given similarly. U2 is this 0 1 0. Here I am in one dimension, so I just put 1 here, meaning that it is the unit vector at the tangent space to R at the point X. What is this? This is the following. I map this vector. This is the unit vector at the point X via the differential of F. Okay. Ondan sonra ne yapacağız? Yeah, dx. Yes. So what is this? This is just okay. It is just it was 2x. So I just multiply this vector by 2x. We get 2x here, and then we take dx of this. It is just 2x times 1 at the point 1 plus x squared, actually. Okay. And then this is a constant, and then dx at the point 1 plus x squared, this is just 1, so we get 2x. And this suggests what? This suggests the following. this okay, f star of dx is nothing but actually df, and f is just being this expression, so d of 1 plus x squared, which is just derivative of this expression, which is just 2x times dx. Okay. In calculus, this is what we write. You know, we make, you may consider this as a variable change. Let's say f of x equal to u, my new variable, u equals 1 plus x squared, and then you say, what is du? Du is just 2x dx. Okay. So this whole thing is nothing but, you know, old variable change formula, nothing new. Okay. If you call this new, the image of this function as your new variable, okay, u equals 1 plus x squared, then du, the one form corresponding to this function, is nothing but the derivative of this times dx. Okay. So this pullback operation is nothing but, you know, a fancy way of writing variable change. Okay, variable change. All right, we will come back to this later. Now I will stop that discussion on one forms. They're a bit confusing, and they should be, because, you know, it's a new language, and you are seeing, you know, something you have already known for years in a different way. That's why it, you know, sounds confusing, but that's okay. Well, let me see if I. Okay. You mean this, to emphasize? Okay. Okay. So like this. Okay. Yeah, 2x0. Now final. Yeah. Okay. Yes. Okay. All right. Well, there is this corollary, but we already talked about that. Okay. For differentiable functions, f and g, the differential of f times g, right? Product of two functions is another function. And since f and g are both differentiable, the product is differentiable. What is the differential of this function? Well, it is nothing but g times the differential of f plus f times the differential of g. So we have a kind of Leibniz rule, okay? These are not, derivatives. They are a little bit different than derivatives, right? This is the differential, but of course it's made of derivatives. However, it is not the derivative. And the proof is as follows. So what is differential of this? Well, differential of this is nothing but derivative of this function with respect to x1 and then dx1 and then dx2 and so on. So it is nothing but this summation. Okay. Now we apply Leibniz rule to this gadget. So this gadget here is just I from 1 up to 3. What is this? Derivative of the product with respect to ith coordinate. That is derivative of the first function times the second plus the first function times the derivative of the second, and then dxi. And when you open this up, you will just get what? Okay, g times I from 1 up to 3 del f del xi dxi plus f times, I can take f outside, right? I first break this summation into two summations and then take f and g outside because there is no index here. So we have this. And what is this? This is just g times differential of f plus f times the differential of g. Okay. Okay. We have another lemma. Let f be a function from R3 into R and h a function from R to R. So let these be differentiable functions. Then we may compose the these two given functions. I may first go by f and then by H, so H composition F, right? And I may talk about, of course, differential of this. Now, this is a function from R3 into R. What is the differential of this? Well, differential is like derivative. So we should have, kind of chain rule. And here's the chain rule. This is just derivative of H evaluated at F times differential of F. And the proof is, again, just from the definition, basically. What is this? This is nothing but I from 1 to 3 partial derivative of H composition F with respect to ith coordinate times dxi. And here we apply chain rule to this partial derivatives. And what are they? Derivative of this composition with respect to xi is nothing but derivative of h. H is a single variable function, so its derivative we may just think, represent it by h prime, and then inside h I have f. Okay. Let me write it this way: times derivative of f with respect to xi, and then I have dxi. Değil mi? Kompozisyonun türevi, right? The derivative of this composition, I take the derivative of h and then multiply it by the derivative of f with respect to xi. But here you see that this expression has no index I, so I can just take it outside h prime of f, and then what is left? Summation of these expressions, well, that is nothing but df. Okay, so we are done. Okay, I have h. Yeah. I have here h of f x1, x2, x3, and I would like to take derivative of this with respect to, let's say, x1, right? Well, h is a function of a single variable, so derivative of this, how would you take the derivative using chain rule? You take derivative of h, well, derivative of h, you put whatever inside you have, and then times derivative of the inside. Derivative of the inside function is f, and derivative of this with respect to the ith variable. So I have this. Okay. Okay, I am, so my time is up again. It kind of goes very fast. Okay. So I'll see you on Wednesday, right? Okay, see you.